welcome Virginia today, who is an expert on surface modeling and has been in various places, studied in Spain, UCLA, Switzerland, Munich, and yeah, I'm really looking forward to hearing about your work.
Okay, thanks for the introduction. We'll present work I did last year at TU Munich, so Technical University of Munich, in the group of Daniel Krumers. And as you see from the title of the talk, the goal was to do shape analysis in a compressed format. Now, shape analysis, we usually analyze surfaces in terms of their geometry. So we are dealing all the time with measurements like normals, curvatures, and geodesics. We use their measurements to have an easy way to analyze the geometry of the surface. And I'm just looking at the geodesic here. So pick the point on the nodes, and I compute the geodesic there. And that's useful for us because if you look at the level lines of the geodesic, you know that closer level lines, when you go hiking, means that it's more steep. And we use these kind of maps to do shape matching or compute descriptors there. Now, when we do that, not with analytical shapes, but we have the data out of computer vision techniques, the things look slightly more complicated because our data is a point cloud, and good luck trying to estimate the curvature out of a point cloud. It would be completely messy. So what we usually do is we first fit a mesh to this point cloud and then do shape analysis there. The main problem with that is that we need to compute first and second order derivatives out of a mesh. And that means that you need very fine meshes in order to have accurate derivatives. And when you do that, then you need very large computational operators to do shape analysis. And that's a bottleneck because things become slower. So what we try to do when we compress shape analysis in a compressed representation, the first idea that comes to mind is like, well, let's just compress the shape, the mesh. So I do an edge collapse, and I get a small representation, and I try to compute geodesics, and you can see they look horrible. But that's not because we cannot do shape analysis. It's not the intrinsic dimensionality of shape analysis or something like that. It's just that our derivatives are very lousy and very poor estimates of them. So what we try to do is to look at what happens when we do shape analysis. When we do shape analysis and we have very large operators, what we usually do is we look at the Fourier analysis, and we take a few eigenfunctions or a few coefficients of your decomposition. And that is just assuming that your shapes or your functions that you're estimating over them are smooth. So the idea was to see if, OK, can we do shape analysis bypassing this large computational mesh and directly fit a subdivision surface or something smooth to the point cloud, and then do shape analysis having derivatives and smoothness for free. That's what we tried to do. And so we tried to just find a shape representation that is well suited for shape analysis. And when we realized that there were not many code that we can just fit it to our point clouds and then do shape analysis. So we had to, most of the work went actually to developing some code and some tools to actually properly fit a subdivision surface to a point cloud that it's more or less robust to noise and outliers. It's computationally efficient. We don't want to be wasting a long time to do the fitting. And then that allows us to still do shape analysis. And that shape analysis introduces some constraints, but not major. And that will be also the outline of my talk. I will first explain why we believe subdivision is well suited for shape analysis, then focus on how to actually fit a subdivision surface to a noisy point cloud, and then see how shape analysis looks with that representation. So just a few words on subdivision. I don't have time to give you all the background. So we'll just give the tools that we need to think about here. So subdivision has a very nice intuitive way to represent a smooth curve as a sequence of subdivision steps that you take to infinitum. So the idea is you start with a control polygon. You subdivide it once. You subdivide twice. And by the 3 times, you already look that things start becoming smoother. So if you pick the weights or the way you subdivide correctly, you can actually prove that you converge to a smooth surface or a smooth curve that you can parametrize in terms of some basis functions. So that's a graphical approach to subdivision. We're interested more in the analytical one, in which you just look at subdivision as a parametric surface or curve that you parametrize with a spline basis. The advantage of subdivision over simply having different spline patches is that you don't have to be careful how do you merge patches, that things have to be differentiable there or continuous or things like that. You just have a control mesh that defines the domain of your parametrization, and you use a spline basis over them that you obtain through subdivision to parametrize your curve. And you get something like that. So you parametrize your surface S as a bunch of, actually, I should use that. Yeah. Spline basis multiplied by some control points, which are the points on your control mesh. And we just believe that subdivision is good for shape analysis because you can use the same spline basis to parametrize over any function g that goes from the surface to the real line. So imagine g is a color map. You can parametrize the color map with some coefficients here, and you have as many coefficients on vertices on the control mesh. And that's actually what I display here. So that's a control mesh we fitted to a horse, and for each vertex on the control mesh, I have a color. And you can see that as you subdivide multiple times and you get to infinitum, you will actually get a surface that is smoother, but also the color map. And just for you to understand what you'll be visualizing, I usually subdivide 3 or 4 times. I take that as a proxy of the smooth surface, because that's usually just good enough for the resolution of projectors. But all the computations are done with a few control vertices, between 1 and 2,000, or sometimes a few hundred. But we're not getting very large meshes. And that's the advantage, because then all our shape operators have a few variables. That's what gets us started on that. Now, the main bulk of the work went into actually fitting a subdivision surface to a noisy point cloud. And so the input of our algorithm is a set of points and some normals attached to them. Those are all noisy, both the points and the normals. And the output that we want is a surface parameterized with a control mesh of our subdivision surface. And we solve that by formulating the problem as an optimization, where we have 3 terms. The first term just tries to say that for each point in your sample, you want to fit the surface through these points. You then try to match the tangent plane of the surface with the normals. You have a regularizer to keep things in hand for shape analysis posteriorly. And then you have some constraints that I will not deal a lot on them here. It's mostly saying that if you have any information of the boundaries of your surface or your point cloud, you should match the boundaries of your points to surface boundaries. And that's useful if you have partial scans, because otherwise the regularizer will shrink everything. And so once you parameterize your surface with the subdivision, it means that the variables of your optimization are both the faces and the vertices of your control mesh. But optimizing over the faces is a combinatorial problem that we cannot solve in a reasonable amount of time. So we split the optimization in 2. We first have an initialization stage in which we set the topology of the control mesh, and we optimize. Well, we just choose the facets of the surface, and then we do a more careful optimization in which we set the variables. We determine the location of the vertices. So you can think of the first stage as dealing with topology, and the second one with geometry.
So F is integers. It describes the...
Yeah. So, yeah.
The triangles or quads.
Quads in our case. So yes, you don't want to optimize over that. The way people approach this task is more in a greedy approach. And what we do is we just merge it into the initialization. That has another advantage, is that the optimization problem is not convex, so having a good initialization doesn't only bootstrap you in terms of speed, it also can get you to the right local minimum, or to a good local minimum. Now, just the state of the art usually either uses a manual initialization, which is great if you get someone to do that for you, or uses a spherical initialization, which is also very generic, so you can fit almost everything there. The main problem is that then you have to evolve the sphere to something very particular, and what can happen then is that you usually have to add other terms to avoid self-intersections, so you have to take very small time steps to avoid self-intersections and developing holes. That's why we went for initialization. So I will just give you a brief overview for that. So the main goal is to estimate the topology of your surface. And if your input is a point cloud, your best bet is to use an implicit representation and say that your surface is a zero-level set of an indicator function. And you can do that with whatever technique you want. We were using Poisson reconstruction, but you can also use graph cuts on octrees or whatever, or whatever you like. Once you have that, you just have to sample this implicit representation in order to get the zero-level set. You can use marching cubes. And then we just did some edge collapse, because usually these meshes are very large and we want small meshes. Another way to do that is to sample more coarsely your implicit representation, but then you don't actually know exactly how many control vertices you have at the end. So you can do that and then have less edge collapse or be more greedy in terms of edge collapse. So once we have that, we have a control mesh that has the right topology. It has the right number of vertices. So we know the first two terms in our previous optimization are more or less fine. But the third one, which is the regularizer, is pretty bad. Mostly because first we have the constraint that our facets has to be quads. And then we want to do shape analysis of them, so they cannot be degenerate. So what we did is we formulated the problem of matching triangles as a perfect on a mesh, as a perfect matching on a graph. And then we just define a cost functional that makes sure that our regularizer doesn't blow up. And what we actually did is for each edge between two triangles, we define for two adjacent triangles, we defined an edge, and we give it a cost, which has two terms. One measures how far the angles are to 90 degrees, so it's more or less a square. And the other is the angle between the normals of the two triangles. So we want to pair triangles when things are flat. If they are very sharp, we don't want to merge them. And that ended up being a very fast initialization. It's the perfect matching runs in milliseconds, and the other one, depending on the size of your mesh. But it's usually under the second. So it was an easy way to fit the right topology and make sure none of the other terms on the energy blow up.
And just to be clear here, the input is a triangle mesh and the output is a quad mesh.
Yes. Yeah. And for the perfect matching, there are more details. You need to make sure that the perfect matching exists. So you need to make sure that the number of boundary, that you don't have boundary corners. You have to do some tricks on the boundaries. But it works pretty well.
Would you need this if you were just doing a triangle-based subdivision scheme?
No. We just went for quads because then we can use quadrature, works better. And
you can use what, which works better?
Quadrature.
Quadrature,
But
right.
loop subdivision also have their problems, so I'm not sure what. Someone told me early on that Cadmore-Clark was better, and I followed that approach. Once your hands are dirty, you usually continue. I think we all do that. Once you do that, you optimize. You can actually optimize over the control vertices. And I've also added here a color map, because in some cases, when you have color, you can also fit color to your subdivision surface using the same spline representation. But what is important is compare ourselves to the state of the art. So the state of the art is something old from graphics, because that's the guys who started subdivision, which works well, and they have done a lot of work in terms of optimization. But usually, they always have very clean meshes. So that doesn't help us when we have our noisy point clouds. And that's work mostly done here, which tries to fit subdivision surface to either silhouettes or depths and measurements. So it's much more challenging. So our contribution is, compared to that, we have robust terms, L1 in terms of L2 or square distances. Here, I think most of methods also use weighted least squares, but we change the optimization. We have something slightly, we believe, more principled and faster. So just before I introduce each term, I will be showing examples of the results. So the first term, just given a point in the point cloud, you try to find the closest point in the surface and say these 2 points should match. Now that means that implicitly you are adding minimization of a bunch of variables which find the closest point in the surface to that, and you say these two should match. And so the only thing we did is we remove the square here, which is what most people do, and we have the distance. So what happens is, what you observe is that helps us not only when the data is noisy, but also when you have errors in the correspondences, because having the wrong correspondence can completely destroy your surface. What happens here when we fit this clean mesh is that on small scales like the lips, you get some point during the evolution the wrong correspondences, so the upper lip and the lower lip overlap, and you end up with self-intersections. So you get stuck in the wrong local minimum. While having a robust term that we have here tends to be more robust to these errors. That's more remarkable when you actually have noisy data. So we also had some small Kinect scans of small structures. What happened is that here the torso is very thin, and least squares tends to shrink thin structures. And the more noise you have, the more remarkable that is. So here we just get the V shape. The others are slightly flatter. And that is a statue of like 4 little guys dancing. And what happens if you fit least squares model of a subdivision is that you lose all the detail on the legs or the shape of the little girl's body. And you can compare it to a fine mesh that we fitted for robust. We still have some trouble with the noise, and the arms were just slightly better on those structures. Now, the second term tries to say that the tangent plane of the surface should be orthogonal to the normals of your samples. And we measure that by the dot product between the normals, t, and the two basis vectors of the tangent plane of the surface at each point. And again, we have an L1 instead of a square penalty to be more robust. And what that bias is that we're able to better reconstruct very sharp structures. You can see that with a least squares model, you don't have a neck on the awl, and we get some extra feathers. So that's useful if you have boxes or things very sharp. But then you might not want a subdivision. So that was me. And the other characteristic of this term is that it's agnostic to the orientation of the normals. So it's the same if the normal is up and if it's down. And that's good if you did a very poor job estimating your normals. It is bad if you did it correctly. What happens is that if you pick not taking into account the information of the normal orientation, ends up having a much simpler optimization objective that we can solve better. So it's this trade-off between having a very accurate model that you cannot optimize or having something simpler that maybe it's not as good, but you can find a better minimum. And in this case, we have a hand soap. And what happens is that the normals on the table are a mess. And you see that if you use no penalty or least squares penalty, you usually reproduce artifacts on the normals on your surface, where it's slightly better. But that's both because the normals are bad and you are on the boundaries. So that you have two things to consider there. And finally, we went for a rather simple boundary constraints and regularization. We just say that given some points on the boundary, we want these points to lie on the boundary on the surface, which just means that once you consider the parametrization of the surface, these points should have some parameters that lie on the boundaries of your control mesh. And the second term is the regularizer that simply penalizes for each vertex in your quad the distance to the neighboring to the vertices of the same quad, so that we'll try to keep it as squarish or circular as possible. And that means that we avoid very degenerate quads that are unstable for finite element computations. Now, what you see down is what happens if you ignore the boundary conditions, which is what most people usually do, is that then the regularizer tends to shrink the points on the boundary. So we thought that for partial scans, it is important. Now, detecting boundaries of a point cloud, it's not an easy task. So that's why we still have rough edges in our surface. So that's mostly about the model that we decided to fit. Now about the optimization. Played a lot with different optimization algorithms, and we ended up settling on this approach. We solved the optimization by sequential quadratic programming. The idea is that you start with the original problem. We use majorize minimize to formulate the L1 terms, which are not differentiable, as a sequence of weighted least squares. And then once we have this problem, which is still not convex, we use an approximation that relaxes it to a convex problem, which is much smaller. And then once we have this convex problem, we can solve the KKT conditions. And the advantage of these KKT conditions is that the matrices here are sparse, and because they don't change much between iterations, you can just warm start an iterative solver because these things are sparse. And it goes very fast. So just a few words about each of the steps. So I like majorize, minimize. I think it's a very simple idea. So you're trying to minimize this bumpy function here. And once you're here, you start by finding a majorizing surrogate of the function, which is something which is always above your function, but tries to follow it closely. And it also should be easier to solve than their current function, because in the second step, you minimize this majorizer. Now, you know that the value of the majorizer and your function are the same here. Now you minimize it, and because it's a majorizer, you know your energy is below. So at each step, you're guaranteed a decrease of energy, and under quite a broad range of assumptions, you can actually guarantee convergence to a local minimum. Now, in our case, we use an inequality that is used for LP norms, or LQ norms with Q between 1 and 2, to write our distance as a weighted least squares problem, in which once you plug it in our approximations, it has this form. It's a weighted least squares problem where the weights are simply given by the majorize minimize principle. Now, this is differentiable, so we have many more techniques to approach the problem. What we still don't like is that it's quite a large problem, because we have all the coefficients of our control subdivision surface plus all the correspondence parameters. And if you have a very large point cloud, you can have 500,000 of those parameters. So what we did is try to get rid of them. So the idea, these parameters come because for each point in your point cloud, you find the closest point in the surface, and you have a hard assignment. So what we did is, for each point in the point cloud, you find a point in the surface S, which is closest. It doesn't need to be the closest. Then we did a Taylor expansion of the energy you're trying to minimize there, and you minimize that, and you just forget about the point. And what turns out that if your energy that you're minimizing is the square distance to a surface, you can write the second order Taylor expansion in terms of this geometry, where d is the distance between your input sample and a point in the surface in the neighborhood. Tau 1 and tau 2 are the principal curvatures of the surface at this point. Rho 1 and rho 2 are the principal radii of curvature, and nu is the normal. And with a subdivision surface that it's twice differentiable, you can evaluate all these functions through your spline basis quite fast. So we did that in order to get rid of these minimization variables, and then be able to have a convex formulation for an approximate problem like that. And once we have that, you can just write the KKT and solve it. That means that we go from majorize minimize to sequential quadratic program, because the approximation kills our majorizing property. But experimentally, it always works. So there might be something more there. We didn't look into it. And so what we ended up is an algorithm that it's quite efficient. To measure efficiency, what we did is we had a bunch of 72 meshes. And they're like 10 cats, 4 centaurs, and blah, blah. They're fine resolution meshes, around 50,000 vertices. And we fitted that subdivision surfaces between 1 and 2,000 vertices. So they are smaller. And of course, we know we'll do some error. So we measure how far we are in terms of Hadoop's distance from our compact representation to the fine mesh. And we just measure how long it took us to get there. And what we observe is that, of course, it was lower than a least squares penalty, the people using graphics. So that's hours. Those are seconds. That's my old laptop, so it's extremely slow, sorry. But we're more accurate. And compared to Levenberg-Marquardt optimizers, which is what most people use, we're considerably faster. That's for 2 reasons, actually 3 reasons. First, Levenberg-Marquardt solves a larger system at each iteration. So we have as many variables in our KKT as the size of the vertices of the control mesh, while on Levenberg-Marquardt you have both that plus the correspondence parameters. So if your point cloud is large, these things become huge. The other is that Levenberg-Marquardt is a gradient-based algorithm. So when they optimize for these correspondence parameters, you just update them to the neighboring quads. while using a majorized minimized surrogate, you can jump much farther. And that actually means that you can usually get to better basins of attraction and you can go faster. Now, there are many ways to speed up a Levenberg-Marquardt, and I was talking to Mariano, who's Jaime here, and he actually told me that the way he gets his to run faster is reinitializing it, which would be equivalent to what we do when we do these, find the correspondences to do the Taylor approximation. So when you do that, you get to a time comparable to ours, maybe slightly slower, because you still keep track of all these variables. But we just believe that using a majorized minimize to find surrogate, it's more principled than heuristically reinitializing Levenberg-Marquardt. And as a user, you know, the reinitialization frequency is another parameter that you don't want to tune, or I don't want to tune. Now, on the other columns, you just see that each term, so using a least square, the square distance instead of the distance gets something which is faster but less accurate, and the tangent information having the normals actually makes us slower but more accurate. So all the terms we have are useful. And what we actually, in terms of optimization, what we observe with Levenberg-Marquardt is also that we all end up in different local minimum. Levenberg-Marquardt tends to get stuck close to local minima, which correspond to over-smooth surfaces without a lot of reinitialization. So that's the kind of meshes we have. You see they're complex. Most detail are at the faces. That's where I'm zooming in. And you can see, oops. Those are clean meshes. I just took the points out of them, for example. And you can see that the lips, the nose, and the ears are usually slightly not as, have slightly, I would say they're over-smooth compared to the real mesh and our method. And the same for the other point clouds. You lose the neck of the owl. You don't have as much texture on the feathers, and the same happens with other point clouds. So we tend to be better at small-scale detail. Yeah?
Sorry, I wasn't, can you just clarify, is this just the solver that's changing or the energy? Are you
I'm using, okay, sorry. I'm taking the same energy. I'm using the majorizing minimize to find the surrogate. And now I'm using either the quadratic approximation to the square distance function or Levenberg-Marquardt to solve it. But we both use majorized minimize to go from an L1 to a differentiable weighted least squares that we can solve. Is that, yeah?
So the difference is in the LM you have the 3n, 2n, it should be 2n parameters, right, for the unknown correspondences?
Yeah, but you have 3 control vertices. So the correspondences are usually by facet and within each quad. So you have 3.
And 2 floats.
Yeah.
Yes.
And then ours it's smaller. So if the point cloud is large, it makes a difference. And yeah, that's the main difference, I would say. And I'm.
So in both cases, because you're doing the this approximation by finding nearby points and second order expansion, the claim is that both LM solver and R solver reinitialize these correspondences only once at the beginning, or both?
So we find the majorizing minimizer surrogate. Yeah. Then I found the approximate correspondences where I do the Taylor expansion. And I solve that with the KKT. In the case of Levenberg-Marquardt, now I take the correspondences I estimated from my previous MM iteration, and I solve that. So there the correspondences.
Or this is the whole optimization?
I think I was running up to certain accuracy. I'm not running every iteration of MM up to full accuracy. So what happens is that with Levenberg-Marquardt, I'm using the previous correspondence parameters. I'm not reinitializing it. So if I reinitialize, I get faster. Right. We still converge to different local minimum. And in some cases, I would say LMs may be smoother. It has this assumption that your residual should be smaller. But you could say that our Taylor expansion also has the assumption that residuals should be smaller. So we both have this problem. The main difference is that in our second order Taylor expansion, we use curvature information that it's not on the LM. But that's why I think we are slightly better on very small curved structures. But but there are all these like what's the name? There are approximations you can add to LM to take into account these things, and I didn't try them. So like fancy or graduated LM, I've never tried. And so once we had that, we can't get to doing shape analysis on subdivision. So I'll be looking at shape analysis with Laplace-Beltrami eigenfunctions. You can think about it as doing shape analysis with Fourier coefficients. And the advantage of that is that when you do shape matching or you compute shape descriptors, all your descriptors or your techniques are invariant to isometry. So it is the same if I translate and rotate the shape rigidly or if it's in the same place. And we're looking at wave kernel signatures, which is a shape descriptor, geodesic distances, and shape matching by functional maps, which is quite standard things that we do in shape. Now, for you to understand what we're doing, I'll be doing all the operations on the control mesh, on the control grid. So we have a few control points. And I'll be visualizing things on a 3-level subdivided mesh. But it's not that we subdivide and we do shape analysis there. Okay, sorry. So Laplace-Beltrami operator is just generalization of the Laplacian. Because I'm short of time, we just skip that. Think about it, generalizing Laplacian. The eigenfunctions of it are your Fourier basis, and we extract them with some finite element computations over the grid. And once we have that, we can compute shape descriptors, like the wave kernel signature. So what we were doing is we had a Tosca database, which has high-resolution meshes and coarse resolution meshes for the same. And we then were trying to get the accuracy of a fine mesh with our subdivision surfaces with smaller than the coarse mesh. And we observed that if you compute shape descriptors, like the wave kernel signature at the point there in red, most of the high-frequency information, which corresponds to this band of the descriptor, is lost if you lose a coarse mesh in red compared to using a subdivision or a fine mesh, which is what you would expect, because you're not very good at computing accuracies or information at high resolution. The same happens if you do geodesics, using geodesics in heat to estimate geodesic from this. Usually I pick the nose of the cat, and you see a fine mesh, a coarse mesh, and a subdivision surface, and you can see that the low-level frequency information of the geodesic is preserved, while for the high frequency, the coarse mesh starts having problems. And the same happens if you do that of the data from your point clouds, and things usually become worse because your meshes are not so nicely structured and the ones from a database. And what you observe is that we fit a mesh, a fine mesh with robust Poisson reconstruction to the point cloud. We collapse this mesh to have something the same size of our subdivision, and when we compute geodesics on them, the high frequency information of the geodesic is completely lost in the coarse mesh, but we're able to capture it. And finally, for shape matching, in shape matching, we just try to match shapes on different poses. So you want the frontal paw to match the frontal paw on all the cats. And we use the functional map technique. So we just took the code from the authors and we adapted so it would work with us. And what you observe is that the fine mesh manages to do the matching correctly. The coarse mesh completely fails, so we got a lot of errors. And with the subdivision surface 10 times smaller, we're able to reproduce the results. 10 times smaller, it means that your eigensolvers will be 100 times smaller. So it has a computational advantage. And to be honest, we still have problems at the tails of the cats because we have extraordinary vertices. So yes, it works, but it's more of a proof of concept than a final technique we can use right now. That brings me more or less to the end of the talk, which we define a technique to do shape analysis in a compressed representation. Most of the work ended up going into fitting a subdivision surface robustly and efficiently into a point cloud, and then seeing how shape analysis translate there. So we went from that to something like that, but we still have much to do, because when we was trying to fit color, what I observed, of course, is that color and geometry are not completely decoupled because you have shades. And once you have shade created by your geometry, you cannot fit RGBD, so you have to do some things more. And so it's still work in progress. And that's it. So, sorry.
Good,
Thank you.
Great. So, questions? I suggest the previous slide is a good idea to have on. Shall I begin? When you're comparing, actually, previous slide? Yeah, so when you're comparing the poly mesh at 1500 vertices to the subdiv at 1500 vertices, you can, of course, just take the polygon mesh, do your graph optimization, and then call that a subdiv, so without moving the vertices.
Yeah.
Okay. Is that what we see? Actually, sorry, previous slide. Is that what we see here? No.
No.
Yeah, so when you see the...
Oh, so here, this one is obtained by quadratic edge collapse of this one.
Yep.
My original initialization would have quads.
Yep.
And might have tinkered a little bit with boundaries, if the surface has boundaries, to make sure a perfect matching exists.
Yeah. And then you could compute geodesics using that viewed as a subdiv.
If I had loop subdivision or something that lives on a triangle, yes.
Oh no, I mean do your graph thing.
Oh,
so,
okay.
Yeah.
Yeah, what happens there is that usually you match very poorly very small scale things. So if you, sorry, let's look at the horse. You can see here that the most error in terms of shape happens on very large structures that the subdivision has to blow up somehow. So when we're trying that on like the ears or like some of these meshes have actually teeth, that was a mess. So it doesn't work very well for small scale details, and that's important because when you propagate the geodesic, if you start from these small scale details, you will start getting errors on the deformation.
So do I understand here, the picture on the left is the converged subdiv mesh control points after fitting.
Yeah.
Yeah. The initial estimate for those control points is just the original mesh vertices.
Collapse. Smaller.
Yeah.
Yeah.
Okay. So
I don't have it on the slides. I have some pictures. They don't look like that. They look much uglier.
the initial vertices look uglier, or the converged vertices?
The converged vertices look much uglier.
Good, yes, that's what you were
saying. Yeah.
Yeah. So when you compute, do shape analysis on a mesh, it's on these initial vertices.
But I don't do subdiv there. I just use the standard finite elements over triangular meshes.
So you could do subdiv there. That would be a baseline, which is how much help was it to move the vertices?
Yes.
Versus viewing the mesh as a subdiv.
Yeah, we didn't try. Mostly because when we look at the vertices, they look so much different that we thought there must be something. But yeah, that's a good point.
Maybe just, I think it'd be maybe interesting.
It's an easy thing to try, so it's a fair question.
Yes, just run the optimizer for 0 iteration.
Yeah, it's like, okay, fine, I'm done.
That'd be cool.
Yeah.
Anyone else?
I guess as far as geodesics goes, there's other baselines like not computing geodesics via the Laplace-Beltrami, so...
I was wondering, sorry.
Yeah, sorry.
You could do fast marching on your triangle mesh, or you could do a lot of work.
Yeah, we were using the heat method because it's very fast.
Sure, but you've done a lot of work to generate a smooth mesh where your fast method works. So
yes, we didn't try to solve the PDE over fast marching. You solve the iconal equation, so we didn't try that for lack of time. So I was leaving the Munich, so it's like, okay, let's get something fast running.
Anyone else?
Yeah. So, for these meshes, like M1, M2, are they the subdivided vertices or the limit positions on the subdivided?
Is the subdivided vertices.
Yes, so your point is if you replaced each vertex by the limit positions, they might look different. They would
they will look different. Yeah, but no. The thing is, like, then you have like 1,000 points floating, and I cannot visualize things there, or I found it very difficult. So the only way I could do that if I sample a very dense point cloud. But then when you visualize these things with MATLAB or something, you just spend hours waiting for it to appear. It's just like, no point. So another way is to just sample the point clouds, sample the subdivision surface.
No, I think what Jing is saying is there's a closed form for the limit vertex.
Yes.
Right.
Yeah,
So
well,
simply replace the vertices by the limit.
Oh, okay, no,
of the
yeah,
vertex.
I didn't try that. That's a good point.
Can we go to page 32?
Yeah, of course.
It's the size of the mesh that's different. That's what I'm asking. Sorry. No, it's too many. Can we go 4 pages? No, continue.
Oh, page 32, not slide 32.
Yeah, this.
Oh, okay, so where do I see the pages?
At the bottom, two back.
Okay.
No.
This one.
That was correct, was it? No.
I think we passed that one.
What's your
So
estimation
what
of the
was-
slide number?
26, my guess.
26?
Forwards.
Oh, forward, sorry. Do you remember what was on the slide?
It's the person hat at the end.
Okay, this guy.
20.
Let's go 27. Sorry.
That's 27?
Yes.
No,
that's
oh, no, this number at the bottom
page.
right. No, there we go.
Oh, it's a cat, sorry, I understood the person.
Sorry, 28 or 26? Yes. That's
Okay.
right, yeah. I'm just saying. I'm just saying the hat, the third row, the second column, the hat looks really small. It's just like the view program, or it's like because it's a subdivision surface. You subdivide several times, it becomes smaller.
No, I think it's me extracting
Okay.
either,
Okay.
I didn't put the, it's beamer, so I might not have put this height by the width.
I see.
Yeah, that's a good point. Sorry.
Right, it's not shrinkage of the.
Yeah.
Yeah, no, it's, I think it was putting the presentation together that.
Thank you.
Okay, if we finish now, we'll be on time, so let's do that.
Okay.
Thank you very much.